everyone and welcome to my channel Maths with Lazy Bee. In this video, we will be discussing a question of uniform convergence. So this is the question that asks you whether uniform convergence preserves uniform continuity or not. So if you have a sequence, the question says that if you have a sequence of functions fn which are uniformly continuous, so your functions are from R to R and are uniformly continuous, these fn's uniformly converge to a function f on R. So it asks you whether f is also uniformly continuous or not. So if you are going to guess it and you understand the concepts of uniform continuity and uniform convergence very well, then your answer should be yes. Just if you are able to guess it through graphs or something, or your imagination, and you think that if f is a function and you choose any epsilon, and if you choose any points on your real axis, then you should be getting a delta which should not depend on your points but only on your epsilon. The moment you choose epsilon, you get a delta such that if you choose a point, you take any point, and for example u, and if x is satisfying like the inequality this, then fx minus fu is less than epsilon. So this epsilon depends on this delta depends on your epsilon, but it doesn't depend on your point x and u. The moment you choose epsilon, you decide you get your delta. So no matter what point you choose, if you're choosing a point here or if you're choosing a point here, and if x is satisfying this, then this will be true. This will definitely hold. This is the meaning of uniform continuity. In continuity, for every epsilon and for any point, you get a delta. But in that case, your delta might depend on your point and your epsilon. But when you talk about uniform continuity, it should not depend on the point, but just on your epsilon. So anywhere you are choosing your point, you're taking your point anywhere on the real axis, and your points are satisfying this, then this will be satisfied. Okay, this is the meaning of uniform continuity. And uniform convergence means that point-wise convergence is happening. That is, if fn can uniformly converge to a function f, real valued function, these are real valued functions. So, for example, these are your some points. Then if it is happening point-wise, then for x1 you might get n1 such that this is happening. fn1 x minus is for all n greater than equals to n1. So, but for x2 you might get n2 which is not equal to n1, and similarly you might get n3. So you don't know. But for uniform convergence, you should be able to get an n such that fnx minus fx is less than epsilon for all n greater than equals to n. So this should happen for this stage should happen. You should receive or you should get this n such that this n doesn't depend on your x. It will just depend on your epsilon. So this n depends on your epsilon but doesn't depend on your x. In point-wise convergence, you might not get a uniform stage. That is the meaning of uniform convergence. You might not get a same stage for which the convergence is happening. If the convergence start for one point at n1, it might not happen for the same point, and it might happen away from n1, very far from n1. And similarly, for you get another point for which the convergence is not happening at n2. It might happen away. And if it is not uniform convergence, you will never be able to get a single n for which this is true. This is true. This should be true. This should not depend on x. That means you should get a state independent of x. So this is the meaning of uniform convergence. So the answer to this question is yes. If your sequence of functions which are uniformly continuous are converging to some function f uniformly, then f is also uniformly continuous. And the proof is this. So this is a well-known result, first of all, that if f1 is a sequence of continuous function which converge to a point to a function f, which converge to a function f, and the convergence is uniform, then f is also continuous. So fn's are a sequence of continuous function which are uniformly converging to a function f. So f will also be continuous. So this is a well-known result. And now in this video, we'll see that f is uniformly continuous as well if fn's are uniformly continuous and the convergence is happening uniformly. So we will divide the proof in 3 parts. First of all, our claim is f is uniformly continuous. And what information do we have for this? That f1 converges to f uniformly, and secondly, these are also uniformly continuous functions. So that means in order to prove this, we will have to use a hypothesis that this is uniformly continuous for every n and the convergence is happening uniformly. But what do we need to prove in order to show that f is uniformly continuous? We have to show that if epsilon greater than 0, then there exists a delta greater than 0 such that for any x and u in R, since the domain is R and f is real valued, so the codomain is also R. So for any x and u in R satisfying x minus mu is then delta, then fx minus fu is less than epsilon. So the moment you choose epsilon, you get your delta, and this delta is not going to change if you change your x and u. If you take your u here, you here, or here, or anywhere on the real axis, or here, then this is not going to change your delta. This delta is going to work for any u and any x, satisfying this. That is the reason I have put delta as a function of epsilon. That means delta is just going to depend on epsilon and not on any point of the real axis. And this is what we need to prove. We need to prove that f is uniformly continuous. So we need to get this delta. Okay. So first of all, we will prove that we will use the fact that fn is converging uniformly to f. What does this mean now? Fn is converging to F uniformly. This means since I have already chosen, okay, so we start the proof. Let epsilon be greater than 0. So here I am starting the proof. And Fn, and in the first part I'm saying that Fn is converging to F uniformly. This is given with the hypothesis. And epsilon by 3 is greater than 0. The reason I'm using epsilon by 3 will be very clear in the third last step. In the last step or the third step. So epsilon by 3 is greater than 0 and the convergence is uniform. This implies that there exists n depending upon this epsilon, since epsilon by 3 depends on epsilon only, because the moment you change epsilon, this changes. So you don't need to mention epsilon by 3. There exists a n belonging to n such that fnx minus fnx minus fx is less than epsilon by 3 for all n greater than equal to n epsilon, and since the convergence doesn't depend on the point, so this n is going to work for all x in R. So for all x in R, this n is going to work. So in particular, fnx minus fx is less than, now I am just fixing this n for all x in R. This happens because of uniform convergence. The second part, in the second part, we use this fn. We know that each fn is uniformly continuous. So in particular, this f capital N is also uniformly continuous. So epsilon by 3 greater than 0, there exists a delta which depends on epsilon by 3 or just epsilon, because epsilon by 3 is just a function of epsilon only. So we have this such that for any xu in R satisfying, because it is uniformly continuous, so the definition is satisfied. Satisfying x minus u less than delta, let us make it delta 1 for now. We have fnx minus fnu less than epsilon by 3. So your epsilon is going to guide your delta 1. It is delta only, but just to give it a different name right now, because delta will be using delta for f. So, okay. So epsilon is going to decide your delta 1, and delta 1 is not going to come or be following your points. It is not going to depend on the points. So that is the reason it is just a function of epsilon, means that it is going to depend only on epsilon. Okay. Now the final last step. Third step. F1 is uniformly continuous, and in order to prove that F is uniformly continuous, we just need to, since we have fixed this epsilon, and epsilon is arbitrary, so we need a delta. We need a delta such that this definition should also be satisfied of F. So now epsilon is fixed. And then we will say that since epsilon was arbitrary, A proof holds for every epsilon greater than 0. So right now, let delta equals to delta epsilon. Delta 1, sorry. The delta that we got for the Fn, we put delta equals to delta 1. And x minus u being r such that, so I am choosing delta as the same delta which I got for Fn function, such that x minus u is less than delta. Now consider this. In this, add and subtract Fnx and add and subtract Fnu. So this is going to be, take this with this. Using triangle inequality, we get the less greater than sign and use this with this. And this together. Okay. Now, using uniform convergence, we were getting this less than epsilon by 3 for all x in R. We were getting this using uniform convergence. And since the convergence doesn't depend on the points, so this is true for you also. And this is less than epsilon by 3 because our points x and u are just are at max this much apart, delta. And since our delta is same as delta 1, which we got specially for Fn, so this is less than epsilon by 3. So finally, we get this is less than epsilon. And since this inequality, this is not depending on the points for any x and u that satisfy this is true. Because for any x and u that will be satisfying this will also be satisfying this. And since Fn is uniformly continuous and this delta 1 is the one which it was working for any points, so this is the reason this being less than epsilon, this delta doesn't depend on the points because this delta is same as delta 1. And for delta 1 was not depending on our points because Fn x minus Fnu is less than epsilon by 3 for any x and u which will be satisfying this. So since it is less than epsilon and it doesn't depend on this delta doesn't depend on the points, so this is uniform continuity. This makes F uniform continuous function. Since our epsilon was arbitrary, so if we would have chosen some other epsilon, right now if we had chosen 0.5, usually epsilon is very small, and if we take 0.005, 0.007, then since epsilon is just a symbol here, it doesn't have any value, so that means it is arbitrary. Arbitrary means it is not going to, it doesn't have a particular value. So it is not going to affect our proof. So this proof holds for any epsilon And that is the reason the F is uniformly continuous, because if we have proven for this epsilon, which was not a particular value, which was not taking a particular value, that means this proof is holding for any epsilon, and hence F is uniformly continuous. Thank you so much for watching this video. Happy learning.